Okay, hello, this is Irfan, and I'm going to present the paper Last Level Cache Side Channel Attacks Are Practical. We start with the introduction and problem statement, basically what is a paper, what is the thing that the paper is offering, and we move on to some background before talking about their implementation, and in the end, there is an attack example explanation and some possible mitigations. So, in a safe world, cloud providers have high resource utilization by co-hosting multiple VMs on a single hardware platform, and the virtual machine monitors isolate VMs and schedule the resources and stuff. However, in reality, co-hosting multiple VMs on a shared physical resource can cause potential interference between the VMs, and a malicious VM may learn information and data processed by the victim VM. So before this work, other works had shown that these types of malicious activities are possible through L1 cache. However, that is not very practical since L1 cache is private to a core and virtual machine monitors do not co-locate multiple VMs on the same core. But in contrast, last level cache is shared among all cores and is a more realistic attack vector. So basically, this work shows that these attacks can be done through LLC. So in the background section, we talk about virtual address space, large pages, and cache architecture. Okay, virtual address space refers to the range of memory addresses that a process can use, which is abstracted from the physical memory. This abstraction allows each process to work with its own independent address space, and then therefore it doesn't need to worry about the actual physical layout of memory. And looking at the diagram, we can see that CPU generates a logical or a virtual address when it's executing a program, and then this address is sent to the memory management unit, which translates it into a physical address. And then finally, in the end, it will be transferred to the physical memory, and then the data will be fetched from there. Okay, so in modern computer architectures, memory is managed using a technique called paging, where memory is divided into fixed size blocks, which are called pages. So basically, a page represents a contiguous range of addresses that maps logical memory to physical memory. And the size of a page determines how memory is allocated and how it's accessed. Typical page sizes include 4 kilobytes, 2 megabytes, and 1 gigabyte. And looking at the diagram on the left, we can see a page that is being made out of a contiguous logical memory. And then on the right, we see how these pages are stored in physical memory. So basically, different processes have separate logical memory spaces, and their pages get mapped to different frames in physical memory. So here we can see that there is a TLB, which is translation look-aside buffer, and it basically is a specialized cache inside the CPU that stores recently used page table entries. Now, each TLB entry basically maps a virtual page to a physical frame, as we saw in the previous slide. And so the thing is that large pages reduce the number of required entries, and therefore they increase the chance of a TLB hit, and consequently they reduce the page table lookups. So because of this reason, virtual memory monitors, virtual VM, actually VM monitors, use large pages for mapping guest physical memory. And looking at the diagram on the top right, we can see that when a virtual address is accessed, the CPU first checks the TLB. If the entry is found in the TLB, then the translation happens fast. Otherwise, the page table must be accessed, which takes some extra time. And even if it was not found there, then it prepares the data to be fetched from the disk. And the bottom diagram shows how larger pages reduce the number of bits used for page offsets, and this basically allows memory coverage per TLB entry. Okay, in this slide, we see the cache hierarchy and how it helps improve processor performance by reducing memory access latency. Cache memory is a small, high-speed memory located closer to the CPU, and it stores frequently accessed data to reduce the time that needs to fetch data from RAM. So since RAM is significantly slower than the CPU, then basically caches work like a bridge that speed up the gap between CPU and the memory. And so modern processors use a multi-level cache hierarchy to basically balance the speed and capacity. And as you can see in the diagram, there is first closest to the CPU, there is the L1 cache, which is the smallest but fastest. Typically is around 32 kilobytes, and with the access latency is around 4 CPU cycles. Then there is L2 cache, which is larger but slower than the L1. And then in the end, we have the L3 or LLC cache, which is larger than the other two and slower. So it basically usually is around in the order of megabytes, and the access latency of it is around 40 cycles. So in this slide, we'll discuss how data is accessed in the cache and the concept of cache lines. Caches are organized into fixed size lines, which are the fundamental units of allocation and transferring cache memory. It basically means that instead of loading an individual byte, the CPU fetches an entire cache line at once, and this is going to improve the efficiency by exploiting spatial locality. A typical cache line size is 64 bytes, and when we access the memory, the address is basically divided into 3 parts, as you can see in the diagram. There's the tag section, which identifies which memory block is stored in the cache. Then there's the index section, which determines which cache set we're looking for. And then there's a block offset, which identifies the specific byte within the cache line. So today caches are mostly associative, which means that memory addresses are mapped to a specific set in the cache. But each set itself contains multiple cache lines, basically W ways or associativity. And when accessing a memory address, the set index is extracted from the address to locate the corresponding set. And then the tag field of the address is used to compare against the tags of all the W lines within the set. And if there was a match, it means that, well, there's a cache hit and the data is available in the cache, can be quickly accessed. Otherwise, this is a cache miss and the data must be fetched from the lower cache level or maybe from the main memory. So since memory is significantly larger than the cache, it means multiple memory lines may map to the same cache set. And if more than W lines map to the same cache set, this means that there are going to be cache contention, and this potentially leads to cache evictions. So the decision that which one of these lines should be evicted is made by the cache replacement policy. There are basically several strategies for doing this, but some approximations of the least recently used algorithm is typically used nowadays. The diagram shows how LRU replacement policy works. And so this is considering a very small cache with the size of 3, but it shows the functionality of LRU. So the cache gets filled as long as there is free space in it. However, when it gets full and, for example, value 4 needs to be accessed, the least recently used value, which is 1 in the cache, will be evicted. And then again, with each access to the cache, the least recently used data will be updated and then evicted if needed. Okay, so in this slide, we'll discuss the concept of cache inclusiveness, which determines how data is shared between different levels of cache. Basically, the inclusiveness property of a cache states that the higher level cache holds a strict superset of the contents of the lower level cache. The diagram shows this basically, and we can look at the diagram C where both caches are in a state where data X and Y are present in both L1 and L2. Then if X is evicted from L1 for any reason, there is no extra thing needed to be done and everything's fine. So later if L1 needed X again, the L1 can access it through L2. However, if for any reason any data like Y is evicted from L2 while it's still present in L1, then L2 will send an eviction request to L1 and also evict Y from L1. So basically, everything that's not present in L2 should not be present also in L1. And this basically is the concept of inclusiveness. And in the LLCs in the modern Intel processors are inclusive. So modern Intel processors use also a more complex architecture for the LLC to improve the performance. The LLC is divided into pair core slices, which are connected by a ring bus, and the slices can be accessed concurrently and are basically separate caches. Although there's a bus there that makes sure that each core can access all the slices. And basically to uniformly distribute memory traffic to the slices, Intel uses a carefully designed but undocumented hash function, which maps the address into a slice ID. And within a slice, the set is accessed as in traditional cache. Okay, so we will dig deeper into the attack proposed by the authors now. First, we need to know the attack model. Basically, the attacker in this attack model controls a VM that is co-resident with the victim VM on the same multi-core processor. The victim VM computes on some confidential data, and the attacker knows the crypto software, and it knows also that the victim is running that. Then no vulnerability in the virtual machine monitor and no specific virtual machine monitor is assumed. And the attacker and victim do not have to share a core or memory, and also attacker does not have to synchronize its execution with the memory. I'm sorry, with the victim. So this slide basically shows the idea of the attack. The method is called prime probe, and the attacker monitors cache usage of the victim process. The key idea is that cache misses take significantly more time to complete than cache hits, and the attack happens in 3 phases. In the first phase, which is called prime phase, the attacker populates the cache with its own data. Then the attacker waits and lets the victim process run for some time. This results in victim accessing some of its secret values, so consequently, attacker's data will be evicted from they'll be evicted from the cache and will be replaced by those of victim. So when the idle time is over, the attacker starts repopulating the cache with its own data again. And in this phase, this time the attacker measures the time it takes to access the data. If it's not taking long, it means there's a cache hit, and those lines were not accessed by the victim and were still present in the cache. Otherwise, if it takes a long time, this means this was a cache miss, and the attacker will understand that those lines were accessed by the victim during the idle time. Now, there are a few challenges for doing prime probe on LLC, which we discuss here. Basically, the first one is that L1 and L2 will satisfy most of the processor's memory accesses, which basically means that LLC has less visibility into victims' memory activity. This issue can be solved by leveraging cache inclusiveness. So LLC can evict a line and consequently evict the data in L1 and L2 so that then memory accesses need to be done through L3. The next challenge is that we cannot prime and probe the whole LLC since it is orders of magnitudes larger than L1. The solution is to find a few cache sets that correspond to the security critical accesses made by a victim and then only monitor those sets. But finding those sets is a challenge itself. The attacker cannot know the virtual addresses, and so the solution here would be that we can monitor each set of the LLC individually and look for temporal access patterns that are like what we're expecting to see from the victim doing a security thing. Then the next challenge is to find a method to construct an eviction set to occupy exactly one cache set. Since we decided to monitor sets one by one, we need to be able to do prime and probe on specific single sets. It is challenging to find a set of addresses for that since the LLC is physically addressed. And also there is the new sliced caches, and it's difficult for the attacker to know which of the slices is being accessed right now. And basically the final challenge is how to extract fine-grained information. This is an issue because the resolution is limited by the speed of which the attacker can do probing on the LLC. And probing on the LLC takes more time than L1 because it's larger, it has more ways than L1, usually 16 ways. And also the latency on LLC is much longer compared to L1. So now how can we construct an eviction set? So large pages become useful here. A 2 MB page is large enough so that all the index bits are within the same offset. This means the translation from virtual to physical memory does not affect the index bits. So the attacker does not need to reverse engineer the full address mapping. However, in recent Intel CPUs, large pages alone are not sufficient to locate the LLC slice. And this is because memory lines with the same set index bit may be located in different LLC slices, which then adds an additional layer of complexity. So this algorithm here constructs eviction sets by searching for conflicting memory addresses for a given set index of each slice. A conflict set is a subset of memory lines that all map to the same cache set. The goal is to find exactly W lines that will conflict in a given set, ensuring any new access causes an eviction. To effectively evict a specific cache line, we need to identify memory addresses that compete for the same cache set. So this is basically done by repeatedly testing memory accesses and measuring access time to detect the conflict. The algorithm first starts by randomizing memory lines and initializing an empty conflict set. Then for each candidate line, it checks if it conflicts with the existing conflict set by using the probe function. And then if the access time exceeds a certain threshold, the candidate is added to the conflict set. And this process continues until exactly W lines are found that map to the same cache set. Next, the algorithm first checks if a candidate still conflicts with the remaining set. Then for each memory line, it verifies whether removing it still causes eviction. And finally, it outputs the eviction set and removes unnecessary lines from the conflict set. So this last part is essential because LLC in modern CPUs use multiple slices. And so it basically means not all lines that initially appear conflicting actually belong to the same cache set because they're in different cache slices. So this slide here shows how prime probe is implemented in the end. To effectively probe the cache, the attacker organizes all memory lines in an eviction set as a linked list in a random order. This random permutation prevents the hardware prefetcher from loading memory lines in an optimized way, so it basically ensures accurate eviction-based attacks. In this code, you can see the register R8 is the head pointer of the linked list, and the RDTSC instruction, which we can see in lines 2 and 17, is used to measure the time to traverse the list. And each of the 12 move instructions read one memory line in the eviction set and stores the pointer to the next memory line. So since each move instruction is data dependent on the previous one, access to the memory lines is fully serialized. And upon completion, register EAX contains the measured time. Also, we can see some elfens instructions in line 116 that protect against instruction reordering and out-of-order compilation. So, in general, it ensures that all preceding load instructions complete before progressing, and that no following load can begin execution before the elfens. Okay, so a covert channel is basically an unintended communication channel that allows two processes to exchange information in a system that enforces security restrictions. And in this context, they are leveraging cache-based side channels to establish a covert communication. To evaluate the effectiveness of the approach, the authors measure the channel capacity, which quantifies the maximum rate at which information can be reliably transmitted through the covert channel. And the experiments basically involves constructing an eviction-based communication channel and testing the ability to transfer data. So here we can see the covert channel protocol. The sender picks two memory lines that map to two agreed cache set indexes, line 1 and line 0, for example. And then for sending 1, the sender continuously accesses line 1 for a specific amount of time, like T mark. And then similarly, the sender continuously accesses line 0 for a time equal to T mark to send value 0. And on the other side, the receiver, before monitoring the sender, should use algorithm 1 to create eviction sets for set 1 and set 0 and be able to access line 1 and line 0. Then, after the receiver gets those, can use prime probe to continuously monitor those two sets. And to maximize the channel capacity, they set the idle interval between successive probes to 0. Okay, the graph on the right show probe timing measurements for different prime probe sequences. The key observation is that peaks in the set 0 occur during troughs in set 1, and this forms an alternating pattern like 1 0 1 0 1 0. And this alternating structure confirms successful transmission as the sender switches between accessing line 1 and line 0. So, well, despite this pattern, the covert channel is prone to errors because of bit loss or insertion of extra bits or bit flips. And the pause duration between transmissions influences this error rate. But there's a trade-off here. Longer pauses reduce errors by giving the receiver more time to distinguish between ones and zeros, but longer pauses also cause basically reduced channel capacity, which in the end means fewer bits can be transmitted per unit of time. Okay, now we will take a look at an attack on square and multiply exponential algorithm. So modular exponentiation is raising a number b to the power e modulo m. This operation is fundamental in public key cryptography and particularly for encryption and decryption. So the algorithm shows how it's computed bit by bit. This means that the execution follow the bits of the exponent e. So since the algorithm performs conditional multiplication only when the bit is 1, an attacker can observe execution time to infer the exponent. And basically, by collecting multiple observations, an attacker may reconstruct the entire private key. So to effectively trace a cache set, they divided execution time into fixed slots of 5,000 cycles. And this duration is short enough to capture multiple probe measurements within a single squaring operation. And within each time slot, they perform 3 key steps. They do prime the cache set. They basically fill the targeted cache set with known memory addresses. Then they will wait until the end of time slot to allow the cryptographic operation to execute. And then in the end, they will probe the cache set by measuring, and yeah, they'll basically probe it and measure the time, and basically will determine if the primed cache lines were evicted or not. So this figure shows the traces of several cache sets. Each line shows a trace of a single cache set over 1,000 time slots. The shaded areas indicate time slots in which activity was detected in the traced cache set. As the figure demonstrates, some cache sets are accessed almost continuously, some are never accessed, and others are accessed sporadically. The highlighted cache sets at line 43 is the only one exhibiting activity patterns that we expect for this querying code. So we can see there, there's a typical pulse of activity spanning 4 or 5 time slots. And the pauses between the pulses are either around 6 time slots for 0 and either 16 to 17 time slots for 1. So we can easily read the beat pattern of the exponent from line 43. And leading from the left, we see basically 2 pulses followed by a short interval, indicating 2 0 beats. And then next pulse is followed by a longer interval, which indicates a 1 bit. And the resulting bit pattern is something like 0 0 1 0 0, which we can see on the slides. Okay, and now in the end, we take a look at some possible mitigations. One of the most effective countermeasures is to design cryptographic algorithms that run in constant time. And this means that the execution time does not depend on the secret values like the example we saw. But this is not always possible. Then the other mitigation is cache partitioning. And in cache partitioning, basically, we ensure that different processes or security domains do not share the same cache resources, which again has its own kind of challenges. And the final mitigation they suggested was to make cache attacks less predictable by randomizing how memory is mapped to cache sets, which again comes with its own kind of challenges. So the conclusion of this presentation is basically to say with minimal assumptions, LLC cache side channel attacks are practical and that we need to make our systems more secure. Thank you.